thank the organizers for giving me the opportunity to give this lecture. And it is really unfortunate that we cannot be there in person. So I will talk about dark matter search. And by this, I understand searches for the organizers for giving me the opportunity to give this lecture. I hear the sound of my voice. Okay, let me continue. So I understand this to be dark matter searchers through their interaction other than gravitational interaction. So basically through their interaction with standard model particles. So the content of this lecture, I will start by a very short recap of why dark matter is a new particle. And then we'll really get to the heart of the topic and discuss mainly searching for dark matter underground. By underground, I mean direct detection, as well as dark matter at colliders. And I will very briefly talk about search for dark matter in the sky, but for sure there will be many other lectures on using photons to search for dark matter. I will not talk about cosmological probes for dark matter other than the measurement of the relic density. I will mostly consider the hypothesis that dark matter is a weakly interacting massive particle, although I will make some comments and give some examples, the case where dark matter is more weakly interacting. So very briefly, we really have strong evidence from dark matter from many scales, but basically it is limited to a gravitational interaction of dark matter, whether it's at the galaxy scale, at the cluster galaxy scale, or at the cosmological scales. But all this evidence raised the question, can dark matter be a new particle? And this is, we will now try to see how we can search for such a new particle. It will be very difficult to talk about these searches if I don't talk about a little bit about the underlying model for dark matter. Why is that? Is because the number of searches that are model independent are much more limited than what you can achieve in the context of a specific model. And this is especially true when you discuss dark matter search at colliders, because dark matter colliders are not really meant to search for dark matter, but rather for new particles. So in that sense, the framework of the model is important. So for many years, there was, theorists had a very good idea what would be this new particle. It would be neutralino in supersymmetry. And despite the fact that it had a huge parameter space, it was very clear how to go and search for it, either in direct detection, indirect detection, or at colliders. But actually, the same strategy that was devised with the neutralino and supersymmetry in mind can be used for a wider class of model. And especially if we restrict ourselves to the case of WIMPs, that is a new weakly interacting massive particle that is stable. But now there are many more possibilities for dark matter, and we can think of them in terms of dark matter production mechanisms, whether they are intermolecular equilibrium in the early universe or not, and classify them in terms also of their interaction strengths. Are they weakly interacting, feebly interacting, strongly interacting, etc. We can also think of models beyond the standard model that are well theoretically motivated. For example, from the naturalness idea. So this was the idea behind supersymmetry. Or we can think of experimentally motivated extension of the standard model, because we know that neutrinos have mass. We know that there have been a few anomalies recorded recently in B physics and G-2. And we're also trying to explain baryogenesis, which cannot be explained in the standard model. Or we can forget about this stronger theoretical motivation, experimental motivation, and just look at simple extension of the standard model that has a dark matter candidate. So this is what I will call the simplified model. So the dark matter searches then become much more wide than just the search for neutralino and supersymmetry. As I said, it is important to not restrict oneself only to a generic property of dark matter, because the underlying theoretical model will allow to best exploit the connection between search strategy, give us information on can give us information on a range of masses, of coupling strength, spin of dark matter, or the nature of the mediator, which is the particle that can couple the standard model to the dark matter. For example, it can be the Higgs, the particle that we know, or it could be a new particle. So this is a general picture of all the different possibilities for dark matter. So I will concentrate in the green area, which the case where dark matter is at the weak scale, although I will give a few examples with lighter or more weakly interacting particles in that range. And I know you will have lectures also, for example, on axions and on other stuff. So let me briefly recall the property of WIMP dark matter that would be necessary to discuss the search strategy. So why are WIMPs good dark matter candidates? Well, first of all, WIMPs are interacting strongly enough with the standard model that they can be in thermal equilibrium in the early universe when the temperature is much larger than its mass. And the equilibrium is maintained by the exchange process between dark matter and any of the standard model particles, as well as the reverse process. But when the universe temperature drops below the mass of the dark matter, the equilibrium density drops exponentially, the production rate is suppressed, and the dark matter, which is denoted here by chi, start to decouple. Eventually, the rate of annihilation will drop below the expansion rate, so there will not be enough dark matter for annihilation, will fall out of equilibrium and freeze out. And its density depends on this expansion rate given by this formula here. Okay. And so this is in picture what is the situation where you have the number density of dark matter, how it evolves with time, its density drops, and eventually it decouples, and its relic density is given by this number here. The stronger it's interacting with the standard model, the less dark matter will have at the end. So basically, the key quantity is this thermally average annihilation cross-section that will determine how much dark matter there is at the end. So we know this number because we know that the relic density should be about 0.1 as determined by WMAP and Planck. And this tells us that the typical annihilation cross-section is 3 × 10⁻26. Now, if you look at just a generic dark matter annihilation process into a set of standard model particle, you can estimate its annihilation cross-section. It will be proportional to the coupling square for the amplitude to the 4 for the cross-section, divided by the mass of the dark matter square. And if you want this to be equal to 3 × 10⁻26, it's actually in picobarn correspond to approximately 1 picobarn. And this is what people call the WIMP miracle, because this is a typical annihilation cross-section that you find from weak interaction. So particle physics independently predicts the dark matter with the right relic density if it's a weak. However, this is a simple estimate, and I will give you many examples where this simple estimate can vary by orders of magnitude. So Einstein had this famous quote, "I believe more that nothing is a miracle," so I will put some question marks on the miracle. So do we always have this 3 × 10⁻26 or 1 picobarn cross-section? Because this really would put very strong constraint on combination of mass couplings of dark matter. Or say differently, will any weak interacting particle lead to the miracle? So when does this simple estimate doesn't work? Well, we'll see many examples where actually there's the resonant enhancement of the annihilation cross-section. By this, I mean that the pair of dark matter particle annihilates in a final state through some resonance. Here I gave the example of the Higgs. Well, the cross-section will be proportional not to 1 over m squared, but m squared over 4m dark matter squared minus mh squared here. So you see that if twice the mass of the dark matter is equal to the mass of the Higgs in this example, you have a huge enhancement of the cross-section. It means that the coupling required is much weaker. It also means then it's much more difficult to search for this dark matter candidate. You can also think that the cross-section would be increased when you increase the mass, because then more channels become kinematically open. So you have a larger set of possibility for final state, for example, when you cross the W threshold, et cetera, et cetera. And also, typically for a spin 1 particle, the cross-section can be a bit larger. Another enhancement can come from T-channel. When you have a small mass splitting between the two particles here, the dark matter and another particle of the dark sector that has a charge. For example, when the annihilation of pair of dark matter in WW, when there is a small mass splitting, will also have a large enhancement. And finally, there's possibility that there are many dark particles, for example, here a charge, this new charge particle that are nearly degenerate in mass, and that has an impact on the Rayleigh density. I will come back to that later. Okay, so after this introduction, what are dark matter searches? This is all summarized in this diagram here. When we see that here on this side, we have the dark matter pair of dark matter particle annihilating into any of the standard model final states. So I've told you that that's what determines sigma v in the early universe, the quantity that we need to be around 1 picobar. The same quantity is also responsible for the signature for indirect detection, where dark matter in the galaxy annihilates in the final state. Although an important difference between the two is that they don't occur at the same velocity. Here we have about 10 to minus 3 the speed of light, whereas in the early universe, there's some thermal energy, so we have to take the average, and the typical relative velocity is large. Now, the same interaction will also determine how dark matter scatter on quark and gluon that are in the nuclei. So direct detection, which looks at recoils of dark matter on nuclei, will probe in this direction. While at collider, there's possibility of search for dark matter by starting from initial state of gluon quarks, for example, at the LHE or E plus E minus an electron collider, and you produce final states with dark matter. So basically, all these interactions are related. In the simplest model, they're exactly related. And they're determined by the interaction of dark matter with the standard model, which is specified within a given particle physics model. Okay, so let me just say a few additional words about the three search strategy, and then we'll look at what can be done. So as I said, direct detection is the elastic scattering of dark matter, or WIMP, of nuclei in a large detector, and the large detector is deep on the ground to get rid of the background, because there are very few events corresponding to dark matter scattering. And what is measured here is the nuclear recoil energy of the target nucleus. And this can be very small because the dark matter has small initial velocity. And this is actually what I consider the best way to show that actually WIMPs form dark matter, because if you see such an event and you can differentiate it from an event triggered by neutrino, then you know that there's a stable particle out there in the universe that can hit your detector. So there's a huge number of experiments that are using this strategy with different techniques. I won't go into the detail because I'm not an experimentalist, but they can look at scintillation, phonon, or ionization. And the largest detector, actually, this is a bit out of date. The largest detector are currently xenon n-ton. And there's also limits that have come. The best limits are from xenon 1 ton and also Panda X. And there's large detector also with argons. And there's also detector which, for example, well, it's not there. It's not even in my list. Pico, which contains some fluor, and it's sensitive to spin-dependent interactions. And we also have here Gamma Libra, which I will talk about briefly, which works with sodium iodide. Okay, so how to compute the dark matter signal in direct detection? Well, an important simplification is that because the WIMP have a small velocity, 10 to the -3, the interaction occurs actually at very small momentum transfer, basically given by the typical velocity of the dark matter and the reduced mass of the dark matter with the nucleus. And this is typically of the order of 100 MeV. So we can describe the dark matter interactions with nuclei or with quarks and gluons in the nucleon by an effective Lagrangian. It's a very good approximation because typically the particles involved are much heavier. So there's only a few possible type of interaction depending whether dark matter is a fermion, a scalar, Majorana fermion, Dirac fermion. So here I give two examples. For Majorana and fermion, we have here the simplest operator, which actually give rise to spin-independent interaction, and as well as this operator, which actually give rise to spin-dependent interaction. And basically, they take place in nuclei with odd numbers of neutrons or protons. So for Dirac fermion, it's the same thing, except there's an additional operator that can induce spin-independent interaction, and it is given here. And here I give a few examples of typical diagram that can give rise to these interactions. For example, often the dominant diagram is due to Higgs exchange because the Higgs interact with quarks and gluon in the nucleus, either directly or at the loop level. And as long as you have a coupling to dark matter, this is often the dominant diagram. For Dirac fermion, there's also a very important diagram, which is due to Z exchange, which gives rise to this operator, which is also very strongly constrained. And depending on the underlying model, you can have other contribution from new particles to these operators. So here it's an example with the SUSY particle. Similarly, for spin-dependent interaction, there can be more than one operator. So here are this is the operator I have given before, and there's also another possible operator that can contribute to that. So with a handful of operators, we can describe the interaction of dark matter with the nucleus, depending only whether it's a scalar, a fermion, or even a vector. And then we can relate this. There's a simple way to relate the coefficient for effective Lagrangian for WIMP quark scattering with those for WIMP nucleon scattering. Those are basically extracted from experiment or computed from lattice. And actually, there have been quite a few progress in lattice in the last 10 years, which has strongly reduced the theoretical uncertainties on these coefficients. So for example, for scalar contribution, the contribution of the quark to the mass of a nucleus, this coefficient basically parameterizes FQ here, parameterizes the contribution of the quark to the mass of the nucleus. So it's non-zero for light quarks, of course, but also for gluons, because of the heavy quark contribution can be expressed in terms of gluonic constant through this relation. And typically, we have these numerical value with some error bars, of course. And you should notice that even though there's no heavy quark in the nuclei, but effectively through their gluon interaction, we contribute. This is the sum of the three heavy quark. It is just as important as the contribution from light quark. But what is measured is actually the recoil energy of the number, the distribution of recoil energy, and depends, of course, on the mass of the detector, the density of dark matter, also on some nuclear form factor, and on this interaction of dark matter with quarks and nucleons that I've just talked about. The additional factor would be the dark matter velocity distribution. That is typically assumed to be of the form given here. And for easy comparison between experiments, it's usually assumed that the proton and neutron contribution is the same. And then one plots the limits in terms of the spin-independent interaction on protons. While for a spin-dependent interaction, one must give both the proton and the neutron contribution. Also, the experiments all have agreed to use the same velocity distribution, which is Maxwell-Boltzmann, with the same default parameters. So just to give you an idea of the current status of spin-independent interactions, these are the limits, and you see that every few years they increase, and now we're awaiting the first limits from Xenon Anton. And there are also projects that, in particular, Dark Side of Darwin, that should improve by a few orders of magnitude. Here in blue is what I call the neutrino floor. Below this area, it's very difficult to distinguish a neutrino signal from a dark matter signal, so it's an experimental science challenge. So the best limit now is found for dark matter mass of 100 GeV by xenon watt ton, and I want you to remember this number is a few 10⁻11. When you go to lighter masses, the incoming dark matter doesn't have enough energy to pass the threshold of the detector, and it becomes much harder to detect light dark matter, and there's a strict loss of sensitivity here. But as I will comment later, it's important to improve this reach because it's very well possible that dark matter lies in this range. This is just a blow up of this region. Okay. Spin-dependent interactions typically are not as sensitive, but experiments like xenon, which are give the best limits on spin-independent interaction, are also sensitive to spin-dependent interaction, mostly on neutron, due to one of the isotopes that constitute xenon, with a much weaker sensitivity to wind-proton interaction. In this region, it is the experiment PICO, which has the best limit. But these are much weaker than the ones coming from spin-independent interaction. Still, they can be a complementary search for dark matter in some particular, especially in some particular situation where, for some reason, the spin-independent interactions are suppressed. And definitely, now with the new results, they can start to probe some of the dark matter models. Okay, so all these direct detection experiments have put strong constraints on dark matter in both spin-independent and spin-dependent mode. I will assume for the rest of this discussion that there is no confirmed signal. So, and I will answer the question, does it mean that winds are out? Not really. And do we need to go to much higher sensitivity to reach below the neutrino floor or beyond? Yes, we might have to. For this, one of the projects is to use directional detections, that is to measure the direction of nuclear tracks to allow to distinguish dark matter signal from the background. And the most advanced project for that is CYGNIS. But to be honest, I have to tell you that although there's no confirmed signal, there are some anomalies, and in particular in the annual modulation signal in gamma that has been there for many years. And there's also an excess in electron signal. So let me just comment first on gamma. So this is an experiment which measure the variation during the year of the dark matter of the signal, and this there's a clear annual modulation at many, many sigma, but what is the origin for it? It is not clear. All competing experiments, we don't look at annual modulation, but just search for dark matter with a much lower background. Do not find this result, so exclude the favored cross-section predicted by Dama. And there were experiments that were designed to reproduce exactly Dama, that is using a sodium iodine detector and looking for annular modulation. So this is the result from cosine 100 from this year, which shows the wind proton cross-section and their exclusion, and compare to the Dama signal. So basically, it's excludes the Dama signal. So what is the reason for this annual modulation in Dama is not clear, but for the rest, I would assume that there is no dark matter signal. Okay, so let's look at the implication of this no dark matter signal, and let's start to look at some simple models. So the simplest model that we can look at is probably the singlet scalar model, which is just a standard model, plus one additional scalar, plus some discrete symmetry, which is Z2, which guaranteed that this scalar is stable because it's the only particle which is odd under this symmetry. In this very simple model, there's one coupling to the Higgs that drives all standard model observable. So here I wrote the potential, and you see that the new coupling here is between dark matter and the Higgs, and this is this coefficient given by written here as lambda SH. So if you look at dark matter annihilation, whether it's annihilation into Higgs, into vector boson, into fermion final state, it's all proportional to this coupling square divided by the mass of the dark matter square, or here by this factor, in the region where the mass of the dark matter is much heavier than the mass of the standard model particle. And what is interesting is that the exactly same coupling enters the direct detection, that is the interaction of the scalar with the Higgs and with the nucleus. So on the one hand, we need a large enough coupling to make sure that dark matter annihilates enough to get the correct Rayleigh density. And at the same time, we cannot have this coupling too large because it will contribute to direct detection. So let's just try to estimate the numbers. Okay, let's see that dark matter is, keep simple, take the dark matter, which is much heavier than any of the standard model particle, then it will annihilate preferably in WW about half the time, in ZZ about part of the time, and in Higgs. So the cross section is just simply given by these coefficient here of lambda SH squared over MS squared. And the spin independent cross section depends exactly on this times a factor, which is the mass of the proton and the mass of the mediator. Here is the Higgs to the fourth power, and this coefficient which describes the quark content of the nucleon. So basically, you see that you can relate these two, and basically the spin independent cross section would be related to the annihilation cross section times this factor. Well, we know that to get omega 0.1, I told you before, this annihilation cross section should be around 1 picobarn. Well, plug in number and you get that the spin independent cross section is predicted to be in the simple model 10 to minus 9 picobarn. But we have seen that xenon, at least for masses of few hundred GeV, exclude the cross section of the order 10 to minus 11. So this is much too large, unless you go to very large mass where the limit from xenon becomes weaker. Or you look at mass near the mass of the Higgs over 2. So this is what I mentioned before, that you can have resonance in dark matter annihilation when the mass of the dark matter is about mh over 2. So now instead of this cross section, we replace by this cross section. And you can have here an enhancement factor, which are much weaker coupling. So what does it give? You see here on the right, a plot of this coupling as a function of the mass of the dark matter. In red is the prediction to get agreement with the Rayleigh density. The value of the coupling that
I had a question, if I can interrupt you.
Yes.
So when we're adding a scalar sector, like are we talking about its what type of wave it will get or anything of that sort? Can we talk about?
So in this simple model, where I impose the Z2 symmetry with the scalar being odd under the Z2 symmetry, it will not get a web as long as the symmetry is not broken.
Okay, fine. Yeah.
There are, of course, other examples where you can have a singlet that give it, I will show the next slide, I think. Give it a web, can mix to the egg, etc. But now I just want really the most simplistic model. So we see here what is the prediction for the relic. And now we see in blue what is excluded by xenon. And you see that almost everything is excluded, except exactly where the mass of the scalar is about 60 GeV, that is half the mass of the Higgs over 2, where the coupling can be much smaller. Therefore, it's much harder for their detection experiment to probe this region. And this is something generic for all dark matter models, which couple to there's always this region where you have possible annihilation for resonance, where it's much more difficult for direct detection. And to the left here, it's the same thing, except it's a log plot, and it just shows what are the value excluded, and it goes to much higher mass. So you see that it's mass above 1 TeV that are already excluded in this simple model. Okay, so then this model is obviously subject to very strong constraints from direct detection. We've seen that there's so far in this model, there's only one way to avoid this strong constraint is to use the fact that you have a resonance, but this resonance can be the Higgs, can be some other new scalar, whatever. There's also what is called blind spot. So it can so happen that there is more than one particle that interacts with the nuclei and with dark matter, and there could be cancellation between the contribution of standard model Higgs and other. There's also the possibility to have a pseudoscalar mediator, because this, the contribution of the pseudoscalar to the effective Lagrangian is suppressed at small momentum, and it's actually something that contributes only at one loop. And finally, it's possible to dissociate interactions responsible for relic density from those that are responsible for direct detection. Okay, so let me go through this. Okay, so just to give a few examples of how you can, in beyond minimal model, escape these strong constraints. The detail of the model is not important, but this is just an example following the question I just had, where we had add to the model a new mediator, so another Higgs, which can get a web and which can mix with the normal Higgs. And in this example, its mass is 300 GeV. So you see clearly that to get the correct relic density, you have a drop in the coupling around 60 GeV correspond to the normal Higgs, and you also have a strong drop in the coupling around 150 GeV, which correspond to the second Higgs. I mentioned also the pseudoscalar mediator that occurs only on one loop. There were calculations done in the framework of specific model that's showing that even if this occurs only at one loop, you can still get prediction for the spin-independent cross-section, which are within the range of not xenon 1 ton, but xenon n ton or some future project. So these are the limits that are given here. So everything that falls within this range here falls within the range, the sensitivity of future detectors. Another way to get rid of the direct detection is, as I said, to uncorrelate the process responsible for dark matter formation and the one responsible for direct detection. So there are a few examples. One is co-annihilation. I mentioned it because I want to show you a few examples. Another one is semi-annihilation. There could also be multiple dark matter. So, for example, there's nothing that tells us that there's only one dark matter particle. There could be two stable dark matter neutral particles that contribute to dark matter. So just let me say briefly a few words about co-annihilation. Suppose that you have a dark chatter which contains not only a dark matter, but some other heavier particle close in mass. that I would call NLSP. These interaction between the two dark matter and the standard model particle keep the two particles intermole equilibrium. And then you can have annihilation of dark matter with the heavier one into standard model for final state. All these contribute to reducing, increasing the annihilation rate for dark matter, or in fact, to reduce the radial density if this process is important. This process is, however, suppressed by the mass difference between dark matter and the next particle. So it goes like exponential minus delta m over t. So typically you need a very small mass difference, typically of a few percent. And it can happen that this contribution increase radial density or decrease radial density. But the point is that these heavier particles will eventually decay into dark matter, so they will not be present to interact with your detector. So they will not contribute to direct detection, but they will contribute to radial density. So there's you adding new parameters, and you weaken this relation between direct detection and radial density. Okay, so I'm going slower than planned, but I just want to say a few words give you a few examples of a supersymmetry case, because I will come back to the supersymmetry in the when we talk about collider searches for dark matter. Basically, supersymmetry was basically proposed to not solve the dark matter problem, but it was a well-motivated extension of the standard model, and under which there was a parity, which is called R parity, which was introduced to prevent proton decay. And this parity actually means that the lightest supersymmetric particle is stable because there's no channel it can decay into. Just flashing rapidly the content of the supersymmetric model. So basically, every of the standard model particle has a supersymmetric partner, and in particular, the partners of the Higgs bosons and of the neutral gauge boson will have spin 1/2 would be neutral, and the lightest of this one would be stable. Okay, so what can direct detection tell us about this supersymmetric model? Here is a plot showing after this from 2017, but this shows the parameter space of the supersymmetric model in the plane of spin-independent direct detection as function of the mass. And you see here the current exclusion. So actually, what we should learn from this with the different color codes is the different colors actually, all the variables models now correspond to the case where you have some coordination with some particle, a heavier leptons, a heavier quark, a heavier gaugino, or you have annihilation through a resonance, which is the one of the heavy Higgs. You should also notice that the direct detection can be much suppressed. It can be below the neutrino floor. Direct detection has also almost ruled out the case of very light neutralino. So here is the prediction from a scan of the minimal model for very light neutralinos that is below the mass of the Higgs. And you see that xenon 1 ton exclude almost everything, and that xenon n ton for sure will either discover or exclude the remaining. But this is in the minimal model. A simple extension can completely change these predictions. You see here the prediction is simple extension of the standard model, and you see that you go way below the covariant neutrino scattering. And you see that also at low mass, there's a possibility for very light neutralino. So it is very important to test this region. Okay, let me skip this and conclude this first part.
Sorry, Genevieve?
Yes.
Hi, could you come back, please, to the picture that you were showing? Yeah, like that. So the black points are the new allowed points by the extension to this minimal supersymmetric standard model?
Okay, so I went fast on this. It's not the point I wanted to make. all the points here are allowed. The points, the color is actually to denote whether these contribute to the Higgs to invisible decay, because I will mention in the collider part that there's possibility to measure precisely the Higgs invisible width. And currently the limit is about 10%. And you see here with the color code that it can go down to a much lower value, but the black points are too small invisible width to ever be measured even in the future projects. But all of them satisfy radial density constraints.
And that is an extension to the minimal?
This is just a next to minimal supersymmetric standard model where you just add a singlet field and its supersymmetric partner.
Okay, thanks.
Okay, just a final word about for this part about direct detection with electrons. So we've talked about scattering of dark matter with nucleus, but in the same detector, dark matter can also scatter off electron. Scattering will ionize atom, which will then lead to a single electron signal, or the recoiling electron can also ionize other atom if it has sufficient energy and will lead to a few electron signals. So this is this actually allowed to extend the sensitivity of dark matter detection below the famous GV scale, which is very hard to do with simple nucleus recoil. And it's basically because if you look at the typical nuclear recoil energy, it's given by the mass dark matter square, V square over 2 mass of the nucleon, whereas the total kinetic energy available from the scattering process is actually mass, 1/2 mass of the dark matter times V square. So here you don't have this mass dark matter over mass nucleon suppression where you go when you go to the very low scale. And actually it was shown some time ago that even re-exploiting the data from Xenon 10, that you could actually put meaningful constraints on dark matter electron scattering for very light dark matter mass. Here it's one from 1 GeV to 1 MeV. I think yesterday you must have heard something about freezing, and so I will come back later, but just to say that this is almost able to probe the preferred region for very feebly interacting massive particle. And of course, new results from larger detectors will actually probably be able to probe this region. So this is really something to exploit, especially that there was an excess electron recoil event that was recorded by Xenon at energies around 2 keV last year. And it's definitely not clear whether it's dark matter. The Xenon paper proposed a few interpretations. It could be due to axions, it could be due to neutrino magnetic moment, it could be due to a light vector dark matter, an elastic dark matter, etc., etc. So at the moment, the situation is not clear, but I just wanted to be complete to mention that direct detection not only gives constraints, but there is also this anomaly that has been registered. So basically, to summarize the direct detection part, the direct detection part, direct detection experiment now strongly constrained WIMP models. Although I tried to emphasize that there were many possibilities to actually weaken the constraint in a variety of dark matter models. I did not talk too much about that, but just want to mention that spin-dependent interaction, although they are less sensitive, they could offer complementary probes. And definitely to cover all possibilities, it's important to reach below the GeV scale. And as I just said, to even go below the GeV scale and to go into the MeV scale, we can exploit the elastic scattering on electrons. So now, before I change topic, let's just take some time to ask some additional questions, if there are any. I can see the chat, so if you write there, please just someone can tell me there is some
Yes.
question.
For the moment, haven't questioned chat. No.
Okay, great. So everything is very clear. Now, let me make just a few remarks on indirect detection. I know you will have some more talks on that. So just for completeness, I will just make a few observations. So indirect detection is annihilation of pure dark matter particles to standard model, and you observe the decay product. So it can be antiproton, positron, photons, neutrinos. So the rate for this interaction is just proportional to sigma v, the typical annihilation cross-section that we get from the relative density, and it's also proportional to 1 over n pi squared, and then the energy distribution from the standard model final state. So the remarks I wanted to make us about this is that in the galaxy, where we have a small velocity, sigma v can actually be different than what you obtain at freeze out. For example, if we make an expansion in velocity, sigma v can be written as a plus bv squared plus other term. So if the b term dominates, definitely what small velocity, you have a much smaller annihilation cross-section. So, and it depends on basically what is the nature of dark matter and what is the S-channel mediator. So typically in the Majorana-Fermat case with S-channel mediator, you have a V square or P wave suppression. But in some other cases, for example, for vector pseudoscalar axial vector interaction, you don't have such suppression. Also, if coannihilation is the dominant process, obviously it has a suppressed cross-section because the main cross-section that contributes to coannihilation is not there to contribute to indirect detection. But it can also work the other way around because it's possible that the cross-section increase at small velocity. This is known as the sum effect. For example, there are loop corrections that can be proportional to 1 over v. And there's also this long-range Coulomb interaction where you have very heavy dark matter particle annihilating and exchanging basically massless vector boson, because at very high energy multitude, vector boson become effectively massless. And you can see that the sum of that you can have some strong enhancement of cross-section as a function of dark matter mass, and you see here that we can have many orders of magnitude increase in the cross-section. So the only remarks I wanted to make is first about the fact that these searches can actually probe the relevant cross-section, supposing that there's no suppression or storage decrease. For example, I just give a typical result, assuming that dark matter annihilates into BB bar, and this is the result for observation of dwarf galaxy, and you see that the typical annihilation cross-section is ruled out for dark matter less than about 80 GeV. There's also an excess in this channel, but I'm pretty sure it will be discussed in other lectures later this week. The other remark I wanted to make is it's about the charged particle channel annihilation leading to antiprotons or positron. Here, the complication is that you have dark matter annihilating somewhere in the galaxy, and then it is subject to diffusion of the magnetic field, to convective wind, which blow it out of the galactic disk. So basically, what the process that you see here is a complicated path before it reaches the detector. So this is then equation describing this behavior with here the source coming for dark matter annihilating to standard model particle. Here's the convection and the energy lost. So for some time, there was claimed to be a large excess in the positron fraction at high energy. This is shown here with at high energy, but there was no excess in antiprotons. So then it was proposed that dark matter would be leptophilic, annihilating primarily in positons. So model independent approach showed that this was possible, but the cross-section would be very large, and it actually would be, even in this case, tension would result from photons, antiprotons, the cosmic microwave background, etc. So most likely this is due to astral source such as pulsar. So what is left is, in the charged cosmic rays, are antiproton. There again, there was an so-called excess at large energies, where you see here in red is the expected background, and in black were the signal from AMS. So if you look at the difference, it looks like there's an excess. But actually, if you start taking into account in the uncertainty in the cross sections, in the propagator, in the solar modulation, you see that virtually there's no excess. So turning this around, you can now start to use this antiproton to actually constrain actual dark matter model. And this was made much easier with the AMS measurement of the ratio of boron to carbon, because they allow to refine the constraints on propagation parameters and therefore reduce the uncertainties, although the uncertainties still remain large. So by doing model independent analysis of dark matter constraint, assuming all of dark matter annihilate into some given dark matter channel, not worrying about the dark matter model, and then including the fit to B over C, you can see that one can obtain strong constraint of dark annihilation, especially in the BB bar channel, although it is necessary to make some assumption about the dark matter distribution. So here is a Navarro Franken-White profile with a density, local density of 0.38. And in these assumptions, all the region up to 500 GeV will be excluded. And in red is the Fermi limit from photon. In the WW also, a large fraction can be excluded, but this limits weaken quite a bit if you look at different dark matter profiles. So here is the prediction from the NFW in the previous slide. And for a generalized model where you take the coefficient to 0 and a different value for this coefficient RS, and you see that the limit in terms of BB bar weaken significantly, although in the low mass region, it is still excluded by antiprotons. So bottom line, indirect detection are a good probe of dark matter. And right now the constraint, especially the dark matter below 100 GeV, assuming there's no enhancement of the cross section. Of course, the picture could be very different if you have the Sommerfeld effect that I talked about. There are still anomalies, but I'm sure you will hear more in other talks. Okay, after these few words on indirect detection, again, I stop to ask for questions before I move to my last topic.
I have a question.
Yes.
The AMS 02, put those, there. Why do they use just bottom anti-bottom and not other quarks, for instance?
No, this is boron and carbon.
No, I mean in below, if you see the upper bounds on the annihilation cross section.
I mean, no, you can do that with any quarks. And basically, if you take ZZ, you have something similar to WW. If you take some other quarks, it's very similar to BB bar. It is just, I mean, usually, if you have something like, if a Higgs is a mediator, the annihilation in BB bar is much larger in another quark because it's proportional to the mass. So people just showed that as function of BB bar. But this is just a choice. Actually, they have looked at all possible channels into standard model finite states, and the limits are similar.
Okay, thanks.
Okay, then let me move to my last topic, which is searches for dark matter at collider. Okay. I will first start to say that collider cannot search for dark matter. I mean, they can search for neutral stable particle, but stable only at the collider scale. not at the cosmological scale. So collider are very powerful in actually probing the property of the new particle, masses, interaction strength, and all this, but they can say nothing about whether this really is a cosmologically stable particle. So to say, you cannot say that you have discovered dark matter at the collider. You can discover new physics. It can be compatible with dark matter, but to be sure that it's dark matter, you would need to have some other signal in either direct and indirect detection. Hence, it is very important to emphasize the complementarity or the possibility to test the same thing two different ways. Okay, now when I talk about collider, I just said that collider are not so good for testing dark matter itself. They're much better for testing physics beyond the standard model. That is, new particles that have charge, color, or particles that are neutral, of course. So this was sort of the initial way that we were doing dark matter as collider, is work within the framework of a new model that solves some of the standard model problem. This new model could have new particles. Some of them could be neutral, could serve as dark matter candidate, as I gave you the example in supersymmetry. And this is realized if you have some, most naturally, if you have some kind of discrete symmetry which is not broken, then the lightest particle, which is odd under this symmetry, would be stable. But this motivation from a theoretical point of view, as I said at the beginning, is started to weaken because there's actually, this is a too restrictive framework, and one should really search for dark matter in all possible ways, not being restricted to one model. So what can be done at LHC? LHC is a PP collider which first ran at 8 TeV, at 13 TeV, and eventually at 14 TeV. And the largest production cross-section are for particles with color or with charge. Neutral particles leave no signature. So the only thing you see in a PP collider is missing transverse energy. So missing energy in the transverse direction that would signal that there's some neutral particle that went out of the detector. Still, within this context, there's a variety of processes for probing dark matter or for probing neutral particle. So let me give examples of these. So let me start with the most model independent example, which are mono jet or mono something, W, Z, and H. And then we'll go through some of the examples where we have other probes of new particle. So this mono search, it's really actually model independent because you're assuming that you have PP collision, you produce two dark matter particles. Of course, there's no trigger for this. They just go out of the detector, you don't see. But you can have also produced in the same process some other particle, for example, initial state radiation of a gluon or a photon. So this is we call mono jet for the gluon or monophotons. Or they could also be initial state radiation of a Z or W, or they could be radiation of these particles through the process here that helps the formation of dark matter. So let's just talk about the monojet. The signature will be a jet plus large missing transverse energy. Why large missing transverse energy? There's of course small and large. There's small and large missing transverse energy, but we need to trigger on something. There's a lot of background, so we to actually detect to make the difference between the background and the signal. Usually, we have to put a strong cut on the missing energy. So people have tried the effective field theory approach that that works very well for direct detection. So you don't assume anything about the underlying model. You just write all possible operators that relate a pair of dark matter to a pair of quarks, and then put limits on these operators. And of course, you can compare this limit directly to the one from direct detection because these are basically the same operators. Except that when we talk about LHC energy and we construct an effective field theory, we assume that all the particles that could contribute here are very large. which was a reasonable assumption when we were talking about direct detection, where the energy exchanges are under a few hundred MeV. But when we talk about TeV scale, it's much more debatable. So actually, it turned out to be more realistic to work within the framework of simplified model. What are simplified models? Simplified models are constructed from the standard model, to which you have a dark matter, as well as a mediator that couples the standard model to the dark matter and some Z2 symmetry. So you have just a small number of free parameters, and you can try to relate actually what you see at Collider with what you see in other search modes. So for example, for the monojet, what would be the typical interaction in this example where you have a vector mediator? Well, this is the typical interaction with some interaction strength of the coupling of the mediator to the quark, another one coupling a mediator to the standard model, and the possibility to radiate a gluon from the initial step. So people have done that. So here are a few results for, let me see, for different mediators. So the case where we have a vector mediator and you fix the value of the coupling, and then you can compare what is excluded at the LHC with what is excluded in spin-independent direct detection, because it all depends on the same parameter. So you see that in the case of the vector mediator, when you have low mass, the LHC is very good because actually there's no threshold issue here. It doesn't care. It can go to very low mass for that matter. So this is the exclusion coming from LHC. These are the exclusion coming from direct detection. And you see that for this particular type of operator, the direct detection is doing orders of magnitude better as soon as dark matter becomes heavy. The situation is a bit different where you have an axial vector mediator, which is sensitive to spin-dependent interaction. But still, the general picture is the same, is that at low mass, the collider does actually much better all the way to a few hundred GeV, and it's only at very high mass where direct detection is right now doing better. Finally, you could look at a pseudo-scalar mediator, which I told you was only loop-induced for direct detection. So there's basically no direct detection, but then you can compare what can be probed at collider with what can be the sigma V that can be probed, for example, by Fermi-Lat limit on Dwarf spheroidal galaxy. And you see that again at low mass, the collider is doing very good, but at heavier mass, the cross-section drops at the collider and then it loses all its sensitivity. I gave you the example where you radiate gluon, but you can also produce a single Z or a single W. So this is the case where you produce here, radiate the Z. And it's basically generally the same picture that I just shown. The limit is not quite as good as for the monojet, but it's basically the same picture. A collider has more reach at lower dark matter mass, and direct detection is doing better at heavy mass. But actually, just this basic model-independent way of looking for dark matter collider is quite limited, because as soon as you start coupling the mediator to the standard model, then you can look at other channels where there's actually no dark matter involved. So coming back to example where you have a mediator, which is a new vector boson, which is called the Z prime. It's, by the way, very well motivated extension of the standard model based on this simple gauge group, onto which you add a discrete symmetry as well as dark matter. So you add to this a neutral parameter or a scalar. And then in this simplified model framework, you just assume that there is some arbitrary coupling of dark matter to this new vector boson and some arbitrary coupling to the fermion. So as far as dark matter observables are concerned, there's the annihilation into dark matter particles, which depend on the product of the coupling, but there's also, depending on the mass, is the possibility of dark matter annihilating directly into this pair of new vector boson. And for direct detection, you have, as usual, the same diagram, but turn around. But when you look at collider, so of course you have this type mono jet, mono Z, etc. type of signature that is described above, but you have also the basic interaction where you just produce this new particle which decays into standard model. And this allows to extend the range that you can probe this model. So a comparison here in the plane where I show the dark matter mass and the new mediator mass, assuming it has only axial vector coupling and given value for the coupling to dark matter and the coupling to quarks. So here is what the exclusion that is set by the mono jet that we talked about first. So this very small region, but you see that if you look for this new Z prime aggregating into quarks, leading to dijet signature, you can extend the sensitivity much beyond what is here shown into from the monojet. By the way, this is the region here in dash where you have exactly, you can reproduce exactly the relic density of dark matter. So basically, up to a mediator of 2.5 TeV, everything is almost excluded. You can think, can I relax this? Yes, you make this Z prime decays invisibly, but then its coupling to dark matter becomes too large and you have the direct detection. So it's not easy to get out of this simple example. So by the way, you can comment that this plot has actually nothing to do with dark matter, and you're sort of right. That is here, when you actually have a missing transverse energy signature, you know that you have a net neutral particle that came out. When you're just seeing how putting limit on Z prime decaying into QQ bar, you're just testing a new physics model. You don't learn anything, whether you have a dark matter or not. But still, it's different ways to probe a specific dark matter model. So I insist again, colliders are very good, but they are really powerful for testing what accompanies dark matter. They are most powerful for that. Okay, let me skip this example because it's very similar. And let me just go to some other signature of dark matter at LHC. So here I will treat as in a bunch different signature involving dark matter, which will show as missing transverse energy, plus other stuff being jets, leptons, B jets, top jets, several leptons, etc. Another way would be to search for invisible decays of the Higgs, if in the case where Higgs decay into dark matter, that is, dark matter is lighter than half the mass of the Higgs. And finally, there's a third possibility, which is interesting if there's actually the particle that is the new particle that is present with the dark matter that can have a charge could be stable or almost stable at the collider scale, so could lead to a charge track in the detector. So to discuss these, because these are definitely model dependent, I will go back to my example of supersymmetry, which is, forget about the details of the model, just know that it's a model with lots of new quarks, not of new color particles, lots of new charge particles, and there's therefore many signatures at LHC. So there are many different channels where you can generate missing transverse energy. Okay, so this was actually the traditional search of for dark matter, because everybody had in mind that dark matter was with a neutrality and supersymmetry. And basically, you had a PP collision, then you produce new particles. The one that you produce most easily are the ones with color charge. They have the largest cross section, but these they will decay to the lighter particles as well as dark matter. This can be a simple decay or it can be a long chain decay. So basically, the signature will be this missing transverse energy plus whatever comes out, some jet, some lepton. So clearly, this is model dependent. And in a model, usually you have all kinds of signatures. But this is also more than the example I gave you of a Z prime becoming into digest, which was completely uncorrelated with dark matter. At least in these examples, although it's model dependent, you still have a signature of a neutral, a new neutral particle that then you have to check whether it fits the property of dark matter. Okay, so just to discuss this and to show you a few results, let me discuss the case of the neutralino dark matter and supersymmetry. And basically, the neutralino is a spin 1/2 particle, neutral. And you have lots of new particles that are charged or colored. So the different signal involve missing transverse energy, plus a certain number of jets, plus of some number of leptons. Also, because quarks of the first and the third generation can easily be distinguished at colliders, you can have more search involving specifically third generation fermions plus missing energy, I forgot to write. There's, of course, the generic monojet, which is always present. And there are these new search, which I did not yet talk about, for when you have long-lived particles. So I remind you why these channels can be very important is that actually, if you look at a colored particle and you look at the different production cross section, so the colored particle here are in blue, red, and purple, and you see that the cross section is much, much higher than those for the weakly interacting particle. This includes also the charge partner of the W boson. This is why it's advantageous, because of the large production cross-section, to first look for colored particles and then look at the decay into some standard model, here quark and the dark matter. But you can have more complicated process like this one, where it decays into a quark and some other supersymmetric particles, etc., etc. So you have signatures involving multi-leptons, multi-jets, some missing energy associated with dark matter and with the neutrino. So far, the limits on spark, I won't go into the details, but they reach about 2 TeV. Although for the third generation, not quite as much. And here we see the ultimate limit is around close to 1 TeV, although the limits weakens a lot, where when you look at the region where there's a small mass difference between the new colored particle and the dark matter. So you would say, what do I learn about dark matter if I search for a new colored particle? Well, actually, it turns out, you remember I showed you a plot of a global fit to supersymmetry when we talked about direct detection, and I told you, well, the only thing left is basically coannihilation. So really what you would need to be able to probe is the region where there's a small mass difference between the stuff and the neutralino. And typically, in a detailed model, it was shown to be that a mass splitting of about 40 GeV will give you the correct Rayleigh density, assuming some properties of the neutralino. Well, you see that this is covered, at least at low mass, but up to about 340 GeV, and for heavier dark matter, there is no probe, even though the stuff, much heavier stuff, can be probed. So this is one of the difficulty of supersymmetry search. What is more relevant of dark matter is if you can actually produce dark matter and their charge partner, in particular, the partners of all the electroweak gauge boson, because it gives you a more direct detection connection with dark matter. The problem is, of course, the cross-section is much smaller. So you can gain here by going to higher luminosity, because here you gain significantly to produce all these electroweak particles, which then decay into dark matter, plus leptons, plus gauge boson, plus Higgs bosons. And typically the limits now also reach for the charge partners around 1 TeV. Although again, you notice that in this region where there's small mass splitting between dark matter and neutrino, there's very few each. So let me get to the last in my list, which was the possibility of probing dark matter through the production of long-lived charged particle. It's actually something that is relevant in the SUSY model. This is why I mention it here, but it's more in many more extension of the standard model where you have a dark matter and where you have a charged particle, which is almost degenerate in mass. You can have these long-lived particles, and also in cases where there is some very weak interactions. So the decay of the charged particle is quite small. So what is these? What search can be applied when the particle is long-lived? Well, it depends on the lifetime of the particle. It can decay, for example, in the detector. So one typical example is you produce a charged particle. It travels some distance in the detector, and then it decays into the dark matter, leading to missing energy, and to some soft ion that you cannot detect. So basically, you have a track in the detector corresponding to the charged particle, and then nothing. So it is called a disappearing track. To help trigger on this, you can use also the fact that you can, for the same process, when you produce this charged particle here, in this example is a charge and a neutral, or you can produce two charged particles. You can also have the initial state radiation of the two. And basically, well, this plot is not too telling. This one is probably better, where you see here the reach of the disappearing tracks as a function of the lifetime in nanosecond or of the distance traveled. So this disappearing tracks works well to probe dark matter up to about 500 GeV in this example for this charged particle that travels all the way to 1 or 2 meters. It's also possible that this heavy charged particle is actually stable at the collider scale, so travel the 17 meters of the atlas detector without decaying. And here there are other techniques to differentiate this track corresponding to a charged particle with the tracks corresponding to a standard model particle. Basically, because the ionization is higher than any standard model particle. So effectively, a detector like ATLAS or TMS can measure the velocity of the charged particle, the ionization energy loss with the pixel detector, and then it can measure the time of flight and have some indication that this charge track does not correspond to a standard model particle. So this way, the sensitivity to stable particle can be extended all the way to a particle that decays outside the detector, not leave at least 10 meters. Just to summarize everything that I've told you about probing dark matter at LHC, I'll just show you a result that was, it's a few years old, it's from 1915, it was done after run 1, but I like this one because it summarized everything. It gives a list of all the possible searches of what it can, how many of, it generates a whole bunch of models and see how many of them are excluded by one of these other searches. And it depends on the nature of the dark matter, whether it's the partner of the U1 gauge boson, of the W boson, or of the Higgs boson. And you see that this search with multi-jet with no lepton is very powerful, as well as a search with monojet. The search, and these searches with disappearing track and long-lived track are rarely occurring because it's rare that you have this small mass difference, but still they can be powerful. So the global picture is this. On the left, it was dark matter before LHC, and on the right, it was dark matter after LHC. So it looks like a laundry detergent commercial where they show you before and after, and you can never see the difference. The difference is actually in the density of point. So this is, it includes dark matter candidate who can reproduce the relic density or only a fraction of it. And it shows that you can clearly show that there are less points here than there. So the LHC has probed several of a part of the parameter space of the neutrino dark matter model under the three assumptions, whether the dark matter is partner U1, SU2, or Higgs. But basically, the full set of range, the full range of mass remains possible. This dips here correspond to dark matter around 45 GeV, which annihilates through a Z, or 60 GeV, which annihilates through a Higgs. Those are the things that were difficult to probe with direct detection. Something I finally did not mention too much, but I answered the question before, is that in addition to these searches, one can also look at invisible Higgs decay. So it means that by you look at the Higgs and you do a global fit to all the properties of the Higgs decaying into different channels. From this, you can deduce how much of it has decayed invisibly. Or you can look at the production of the Higgs in association with a W and a Z. So you trigger on the Z and you see missing energy on the other side. This gives you a limit on the invisible Higgs decay, which allows you to probe this region here at small mass. Okay, so this more or less concludes my discussion of the WIMP at Collider. Now, in the last 10 or 15 minutes, I want to make a few comments about dark matter that could be lighter or more weakly coupled, because in this case, we have other probes, in particular at Collider. So first of all, I'm not sure if you heard about that yesterday, so let me just repeat. If you assume that dark matter particles are very weakly or feebly interacting, then there will not be intermolecular equilibrium with the standard model in the early universe. So if you recall, I briefly mentioned the equation for which drives the number density of dark matter. It's here. It depends on the expansion rate of the universe and on the annihilation cross-section. And basically, you have two processes. You have depletion of dark matter due to annihilation to standard model particle, and then you have the reverse process creation of dark matter from standard model particle annihilation. Well, if it's feeble, there's very few dark matter in the universe to start with, so you can neglect this term. And basically, the way you produce dark matter is through annihilation or decay of standard model particle in the early universe. The coupling can be very small, the interaction can be very feeble, but you have since the beginning of the universe to produce this dark matter. So basically, this equation will, and you'll drop this term and you'll just have the standard model annihilation into dark matter and the decay of some particle in thermal equilibrium with the standard model. So it can be a standard model particle like a Higgs, or it can be some new particle in thermal equilibrium. So as opposed to WIMPs, where the larger annihilation cross-section, the less dark matter you obtain at the end, here it's the opposite, because you start with no dark matter, and if you increase the interaction strength, you will end up with more and more larger abundance of dark matter. So this is a plot of the abundance of dark matter as a function of time. And here are the curves corresponding to different interaction strength, with interaction strength increasing here, and this is the equilibrium density. Usually when the decay becomes possible, it is the term that dominates, and this is the equation that one has to solve for dark matter. So basically, the dark matter abundance will be directly determined by the decay of this heavier particle. So let's be specific and first let me make a remark to say how we search for these feebly interacting massive particle films at Collider. So despite the fact that it has small couplings, they could lead to some interesting phenomenology at the Collider. And the most relevant is the case where dark matter is produced from the decay of a heavier particle, and that this heavier particle is in thermal equilibrium. So for example, this heavier particle could be weakly interacting and eventually decay into dark matter. So because this one is weakly interacting, it has large production cross-section, but because it has small coupling, it will, to dark matter, it will live long. Therefore, give the typical signature of long-lived particle, that is particles that are either collider stable or decay within the detector, but not at the interaction point. So they give rise to what we say displaced vertex. So we already talked about disappearing tracks, but we can also talk about displaced leptons, where, I mean, there's interaction, you produce this new particle, it travels a little bit, then it decays. So to give you a concrete example, let me again, because I'm talking about collider, I have to talk within the framework of a specific model, and let me talk about the minimal model, where you have only one dark matter, a discrete symmetry, Z2, which make this particle standard, this stable. This particle is a gauge singlet. It doesn't thermalize in the early universe, but it must interact somehow. So the simplest solution for adding this exotic field would be either to use the Higgs, but there would be actually no observable signature, or to introduce a new particle, which is also odd under Z2. Otherwise, it would be mostly coupled to standard model. So for example, it could be a vector-like fermion singlet with a dark matter, which is a scalar singlet. So basically, we recover here the first part of the Lagrangian that we had in this scalar singlet model, but we add to this a fermion and a coupling between the fermion and the scalar, which is given by this coupling here. And is this thing here that has to be tiny for having feeble interaction and having the correct production of dark matter. So basically, there's only a handful of parameters: the mass of the scalar, the mass of the fermion, and the coupling. So how do you search for it at collider? Well, you produce this new fermion, and then it decays into a lepton or scalar. In my example, it's a lepton. I just show you two transparency ago, that the dark matter yield would depend on the partial width of this fermion. So with the actually the typical coupling that gives rise to the correct radical bonders actually naturally lead to a long-lived particle that goes out of the detector, but it would be possible if you lower the reheating temperature, so don't give as much time to create this dark matter, to have at least something like a displaced vertex, so some particle that decays within the detector. So the lifetime could vary under this assumption from a few centimeters to many meters. So with larger than 10 meters, we're in the search for heavy stable charge particle. From a 1 millimeter to 10 meter, we're in the realm of disappearing tracks and displaced vertices. And for larger coupling, these are just regular searches for new particles. Oh, sorry, I missed one. Just wanted to make a comment. What is this displaced vertex? Just give an example where you produce a TT bar. It decays into bottom an electron that you see goes in the detector, a bottom and a muon, and then you can reconstruct the tracks and check whether the two tracks come back to a single interaction point, or whether there's a distance between the interaction point of the two tracks, meaning that the two particles that you have produced have traveled away before decaying. So this is what we call displaced vertex. So just to give you in this specific example, you can have all kinds of signature where you can have heavy stable particles where the lifetime is very large. This is a plot of the lifetime as function of the mass of the new fermion, not of the dark matter. And the dark matter mass is and the reheating temperature are varied here. So let me see. the default value is have a very light dark matter with a high reading temperature, and this is the region where you reproduce the relic density. So you see that the current limits from disappearing tracks rule out part of this parameter space. These lines correspond to having again omega h squared 0.12, but following different assumption, varying the reading temperature or the mass of dark matter. So the more you increase the mass of the dark matter, very soon you're in the region where the only probe is the search for heavy stable particle. Okay, this was just an example, just to show you that you have not only possibility to probe WIMPs, but also to probe feebly interacting particles. So let me take the few minutes to also to say just a few words on a new field, very active, which is searches for very light and or feeble dark matter. When I just argued that they can naturally satisfy the relic density, at least within the freezing mechanism. So in this case, except for the few examples I have given before, most of the standard collider search are not useful. So one has to rely on additional probe in the conventional detector, or use new projects where actually detectors are put a distance away from the interaction point at the LHE. Or one can use a fixed target experiment using one of the beams coming from an experiment on the target and producing new particles this way. Or for very light particle, look at meson decays, for example, K decays, where you can actually produce this very light dark matter. So there's been a lot of efforts recently in a big report summarizing all different searches for these light dark matter. And usually the model that is used to make a comparison is what is called the dark photon model, which is a new vector boson. So which has this kinetic mixing with the U1 of the standard model. So this term here, epsilon, that this coefficient can be very small. Now this is the photon that could be dark matter, but could also be the mediator that couple with dark matter, which could be the fermion or a scalar. So you can add to this a fermion or a scalar. Or you can also, you should have seen by now that to get very powerful probe of these new physics model, dark matter model at collider, it's easier if you have not only dark matter particle, but another particle that you can produce more easily at collider. And this is a case study where you have actually adding not only the dark matter, but a new particle that couples to this dark photon with some coupling like that. So these two models have been used for comparison. So just to give you an idea of the searches that can be used, for example, at NE64 at CERN, you use an electron beam, scattering it on a fixed target nucleon. Then you can emit a photon that mixes with the new dark photon A prime that decays invisibly. Another possible search is in K decays into pions, and the pions decay also into this A prime invisible. And there's this new deplace detector that I talked about. Some have been approved, like phaser. It's some detector which would be 480 meters away from the interaction point with a very small decay volume. And there are plans also for much larger detector, for example, Methuselah, located about 150 meters from the interaction point, could be around 25 meters, and CHIP about 70 meters. And of course, you can also have the same fixed target at electron colliders. So what is the status? Just a few comparisons. Production of this heavier particle with a long lifetime decay into dark matter in the space of the kinetic mixing as a function of dark matter mass for choice of the dark photon mass and mass splitting. This is the value that is predicted to get the explained dark matter. And these are the plans for probing this region by two of the detector. Here is the one from phaser and from Okay, this is just an example, just to give you an idea that there are other ways to probe even these feebly interacting particles. As this is the other example where you don't have this, you only have a scalar dark matter, and then you can look for it either in NF64, as I mentioned, in the ship experiment, or at electron collider. And again, this is a plot of the effective coupling involving the kinetic mixing and the coupling of dark matter to the dark photon, as well as the mass ratio, the region favored by the Higgs density. And you see that some of the region is already excluded, and some of the future project will probe most of the region. Okay, so let me conclude with all these remarks. That first of all, dark matter search is a very active field. There's lots of experiment running, lots of plans for the future, and dark matter candidates are being probed with current experiments. Although the content of the dark matter, whether the dark matter is a single particle or it has partners which are either charged or nearly degenerate in mass, have a very strong impact on the most relevant searches. Of course, the astro search, by this I mean direct and indirect detection, will be the best hope for a signal for dark matter, while colliders has the extra handle that allow to get the properties of these dark matter. So I showed you an example where you had a clear complementarity between direct and indirect search. And I also told you that WIMPs are not the only possibility. Dark matter can be much lighter, much more feeble interacting. Although there are various search plans, it's definitely important to improve the sensitivity of direct searches to light dark matter. In this talk, I didn't talk at all about alternative cosmological probe of dark matter, but especially in this region of light dark matter, cosmological and astrophysical probes can be very relevant. But okay, I had enough material to cover. I did not add this in the talk, but you should keep in mind that these can be important as well. Thank you.
Okay, thanks a lot, Niev. We have some questions in the chat that I can read for you. But first, some question with microphone.
Yes, I have a question. Genevieve, can you go to this plot that you show for the FIMP dark matter with the fermion portal? Yeah, the previous one. Yeah, that one. My first question is there a way to constrain that parameter space using indirect detection or direct detection?
Okay, in some cases, you can direct detection can be sensitive to freeze-in. I had the plot, but I didn't have time to show it. But typically, those occur when you have, for example, a very light mediator. For example, you can think of the case where you have an extra scalar that is very light. If you think of an extra, because the direct detection cross-section is proportional to 1 over m to the 4th. So if you take this mediator to be below 1 GeV, even though the coupling to the mediator can be very small, you can end up having a reasonable cross-section. But for this case, where the mediator is heavy, I don't think you have a signal.
Mm-hmm. And for indirect detection?
It's the same. It's the same. In this one, we don't have signal.
And my last question is, you showed this example in which a FIMP dark matter can be tested at a collider via this charged fermion or vector-like fermion. Do you know if there is a chance to test at in the same picture instead of a vector-like fermion, just using particles from the Higgs portal, for instance. Let's say two scalars, two singlets, in which one is the mediator, which couples weakly to the standard model, and the other component is feebly interacting. It's just a question. I don't know if
I'm
there
not
is a
sure.
possibility.
I'm not
Okay.
sure. I'm not sure.
Okay. Okay, that's all. Thanks.
Okay, one question in the chat is, what could be the hint to discriminate the possibilities in xenon 1D excess?
You mean assuming that you have the xenon, the excess in electron scattering?
Yeah, it's a question from Lorenzo Marafato. Lorenzo, if you want to extend your question, if you are there.
I think what he's talking about is this. And I said that there were many possible interpretation, and the question is whether it would be possible to distinguish some of them.
Mm-hmm.
Okay. I think distinguish some like neutrino magnetic moment or light vector and elastic dark matter would be quite difficult. Would be what the problem with direct detection is you have one signal. This only this excess, and you can fit it. The question is more whether you have additional probe of the same new physics in other ways that allows to distinguish this. What I said about probably the easier to distinguish would be the tritium, because it has a specific signature, but right now I cannot go into the details. But my feeling is whether it's this excess in direct detection on electron or a potential excess in direct detection with nucleon, it's usually quite difficult to get information on the dark matter. I mean, if its mass is similar, for example, in nucleon, if the mass is similar to the mass of the nucleon, you can get some different shape of the nuclear recoil. But as soon as you get to high mass, the difference is so small that it's very difficult to make the difference. So back in the days, like 10 years ago, when we were all hoping to see a dark matter signal and we were thinking that the large detector would be able to make precision measurement, there were some detailed study of how you can actually do that and get information, for example, on the mass of the dark matter particle and differentiate between two of them. But now that we know that we have a much lower direct detection rate than expected, it's become much more difficult to differentiate the different dark matter particles. This is why I've been trying to emphasize that the importance of having two different modes to actually now be able to check the properties of dark matter more carefully.
Exactly. Well, we are in time. Maybe we have to finish here. And of course, if you have a question, you know that I can continue asking in GatherTown and also for email. So it's just we have to finish now, but it's possible to continue later. Okay. So thanks a lot, Genevieve, again, and see you. Okay.
All right. Bye.
Bye. Well, for the student, we continue after lunch. Okay. See the program, please, on the website. Bye.